Hi guys, welcome to Science World Podcasting. Myself Virendra Kumar, professor and scientist. And in these podcasting episodes, I am going to tell you about the lasers, various lasers phenomena, and its important applications in different sectors. So let's start. It is more than 62 years since the first laser was realized. Lasers emit coherent electromagnetic radiation, and ever since their invention, they have assumed tremendous importance in the field of science, engineering, and technology because of their impact in both basic research as well as in various technological applications. Lasers are ubiquitous and can be found in consumer goods such as music players, laser printers, scanner for product identification, in industries like metal cutting, welding, hole drilling, and marking, in medical applications, in surgery, and in scientific applications like in spectroscopy, interferometry, and testing of foundations of quantum mechanics. The scientific and technological advances have enabled lasers spanning time scales from continuous operation up to as short as 100 attoseconds, wavelengths spanning almost the entire electromagnetic spectrum up to the X-ray region, power levels into the terawatt region, and sizes ranging from teeny few tens of nanometers to lasers having a length of 270 kilometers. Now I'm going to tell you about the properties of lasers. Basically, the light from both a laser and any ordinary source of light is electromagnetic in nature, but laser light can be extremely monochromatic, highly directional, and very intense. Apart from these, laser light also differs from light produced by thermal emission in the basic quantum properties. Light from the laser arises primarily from stimulated emission and the resonator cavity within which the amplifying medium is kept. Lasers are having the special properties just like directionality, spectral purity, high power, and extremely short pulse duration. In the directionality, the light from a source of light such as torchlight diverges significantly as it propagates, but the beam coming from a laser in the form of a pencil of rays and seems to propagate without any divergence. The laser beam also diverges, but by a much smaller magnitude. The wave nature of light imparts an intrinsic divergence to the beam due to the phenomenon of diffraction. Thus, unlike a torchlight where the divergence is due to the finite size of the filament, the divergence of the light laser beam is limited by diffraction depending on the laser types and can be less than 10 to the power minus 5 radians. Friends, this extremely small divergence leads to the many application of the laser in surveying, remote sensing, lidar, etc. Because of highly directional properties of the laser beams, they can be focused to very small areas of a few micrometer square. The limits to focusing are again determined by diffraction effects. Smaller the wavelength, the smaller the size of the focused spot is. This property leads to the applications in laser surgery, material processing, compact discs, etc. Lasers have spectral purity, as laser beams can have an extremely small spectral width of the order of 10 to the power minus 6 angstrom. Compare this with a typical source of sodium light which has a spectral width of about 0.1 angstrom. The stimulated emission process, coupled with the optical resonator within which the amplifying medium is placed, is responsible for the very small spectral width of the laser. Because of high spectral purity, lasers find applications in holography, optical communications, spectroscopy, etc. Lasers are having the high power because lasers can generate extremely high powers, and since they can also be focused to very small areas, it is possible to generate extremely high intensity values. At intensities such as 10 to the power 21 watt per meter square, the electric fields are so intense, so high that electrons can get accelerated to relativistic velocities that leads to very interesting effects such as the areas in scientific investigation of extreme conditions and having the power lasers 10 to the power 5 watt and pulse lasers having a total energy of 50,000 joule have applications in welding, cutting, laser, fusion, Star Wars, etc. I am going to tell you about the coherence properties of laser light. There are two types of coherence in the laser light. First is the temporal and second the spatial coherence. If you want to watch the detailed derivation for the laser light and its derivation for the Einstein coefficients, I will provide a video lecture on that and you can watch that video lecture on the Sai Academy. I will provide the link in this podcasting. You can check it and watch the videos, prop thorough videos on the laser light and its derivation. Now I am going to tell you about the some physics concept used in the laser that are stimulated absorption, spontaneous emission and stimulated emission of radiation, population inversion and pumping. So what is absorption of radiation? Friends, an atom can exist in a number of quantized energy states characterized by integral numbers. If it is initially in a lower state and it can be raised to higher state, then by absorption of quantum of radiation, a frequency given by nu is equal to difference in energy levels of the two levels divided by the Planck constant, then this process is known as the stimulated or induced absorption of radiation. The absorbed photon is the stimulating photon. The probability of occurrence per unit time of this absorption transition from level 1 to level 2 depends upon the properties of states of level 1 and level 2 and is proportional to the rate at which photon of the frequency nu fall on the atom, and therefore the spectral energy density of the incident radiation is given by probability proportional to energy density that is equal to the Einstein coefficients of absorption of radiation multiplied by the energy density. Now, what is the spontaneous emission? Friends, let us now consider the converse process. Suppose an atom is in a higher energy state to observation so that its lifetime in this high state is usually very small, that is equivalent to 10 to the power minus 8 seconds, and it of its own accord jumps to a lower energy state, level 1, emitting a photon of frequency nu. This is spontaneous emission of radiation. If there is an assembly of atoms in the system, the radiation emitted spontaneously by each atom has a random direction and random phase, and therefore the incoherency is there from one atom to another. The probability of spontaneous emission from higher level 2 to lower level 1 is determined by the properties of states 2 and state 1. Einstein denoted this probability per unit time by the Einstein's coefficient of spontaneous emission of radiation A221. Einstein considered the equilibrium between radiation and matter in a black body chamber at a constant temperature in which exchange of energy takes place due to the absorption and emission of radiation by the atoms. He found that the stimulated absorption and spontaneous emission alone are not sufficient to explain the equilibrium correctly. So he introduced the third phenomena, that is the stimulated emission or induced emission. So friends, we will know about what is the stimulated emission. According to Einstein, an atom in an excited energy state may, under the influence of the electromagnetic field of a photon of frequency nu incident upon it, jump to a lower energy state and emitting an additional photon of same frequency nu. Thus, now two photons instead of the initial one move on in the system. This is known as stimulated or induced emission of radiation, also known as the negative absorption of radiation. The direction of propagation, friends, here is very interesting. Energy, phase, and state of polarization of the emitted photon is exactly the same as that of the stimulating photon. In other words, the stimulated radiation is completely coherent with the stimulating radiation. As a result of this process, radiation passing through an assembly of atoms is amplified. Thus, the probability of stimulated emission transition from higher level 2 to lower level 1 is proportional to the spectral energy density of the stimulating radiation and is written as in terms of the Einstein coefficient of stimulated emission of radiation multiplied with the energy density. Therefore, the total probability for an atom in state higher level 2 to drop to the lower level state 1 is therefore given by the summation of the Einstein coefficient of spontaneous emission of radiation plus the probability of stimulated emission transition. Now I am going to tell you about the population inversion. Friends, as you know that under ordinary conditions of thermal equilibrium, the number of atoms in higher energy state is considerably smaller than the number of atoms in lower energy state. Therefore, if, however, by some means a large number of atoms are made available in the higher energy state, the stimulated permission is promoted, and the situation in which the number of atoms in the higher energy state exceeds that in the lower state is known as the population inversion, and that is achieved by the phenomena of pumping. Thus, the pumping is the process of achieving the population inversion. Therefore, on various type of pumping process, but the most natural is the optical pumping, which is utilized in the Ruby laser. Friends, there are different levels of the laser system. That is two-level laser system, three-level laser system, and the four-level laser systems. Friends, the details video with the mathematical derivation I will provide in the Sai Academy video lecture, and I will provide the link in the description of this podcasting lecture. So please stay tuned. Thank you.